Hi, I'm Amr Musa. I'm the project manager for North Carolina State University's Underwater Robotics Club. Today, I'd like to talk to you about our underwater autonomous vehicle, Seawolf 8, and a little bit about our competition strategy for RoboSub 2022. This is our AUV, Seawolf 8. We designed it to compete in RoboSub, and specifically, we designed it for this competition run. First, we go through gate. Then we follow the path over to the buoys. We touch one of the buoys, and then we navigate to octagon and surface. That was our competition plan, and in order to do that, we needed to design an AUV that could do a couple of things really well because there's a lot of common threads between each of those tasks. So first, we needed to have a reliable AUV that could move around the water. We also needed it to be able to visually detect objects and navigate to those objects that it visually detected. And lastly, for the octagon step, we needed to have an acoustic system that could detect pings underwater and navigate to the pinger. Now I'm going to hand it over to some of our members to talk about what they did on their sub-team to design a robot that could accomplish those tasks that we talked about.
Hi, I'm Nolan Canigallo, an incoming graduate student in aerospace engineering and the mechanical lead of the Underwater Robotics Club. Seawolf 8's mechanical system consists of a modular aluminum frame with 3 printed brackets housing our electronics hull, 2 battery hulls, 8 thrusters, and 2 depth cameras. The frame provides mounting points for peripherals, protects the electronics hull from impacts, and has 2 internal bays with hinging doors to mount our external battery hulls and other components. The hulls are made of aluminum to withstand the impacts and loads that Seawolf expects to experience. Electronics are secured within the hulls using 3D printed mounts. The thrusters are attached to the frame using machined aluminum mounts, effectively carrying the loads during operation and distributing them over frame sections. Finally, machined aluminum enclosures with acrylic windows and 3D printed mounts house our 2 depth cameras. These designs are modular to support use in alternate orientations for the path and buoy tasks. Together, these systems provide a robust mobility solution and platform for the other subsystems.
Hi, my name is Daniel Mitchum. I am a graduate student here at NC State University in computer engineering. I am the president of the Underwater Robotics Club as well as an electrical team member. The original electronics design for Seawolf 8 was focused on creating a stable platform that would allow the teams to collaboratively develop the robot towards the competition-worthy vehicle that Seawolf 8 needs to be. This is opposed to previous electrical designs which were heavily custom and caused a lot of roadblocks for the other teams as well as the progress of the vehicle towards competition worthiness. This year the electronics team chose 3 strategic improvements to make to the electrical system which would help us work towards our competition tasks. Firstly, we upgraded our power system to include a load balancing scheme. This included taking the main large battery in our hull and splitting it into 2 batteries, which we balance the load of the robot system between them, and we've moved those outside of the hull. This provides us with longer runtime in the water, it removes the danger of the LiPo battery in the main hull with the rest of the electronics, and it frees up space within the hull. Secondly, this extra space in the hull and a new power system dictated the reorganization of our electrical system. We took the opportunity here to move some components around and make room for future systems that need to fit within the hull, as well as implementing an in-cap interface system which moves all of our connectors into an in-cap that seals with the main hull rather than plugging things individually when we want to seal. The final strategic change the electronics team implemented was to remove one of our custom components we call the opto isolator board and replace it with a high side switch. The purpose of this board was to isolate thruster and system power. When we upgraded our flight controller to a new model, we found an incompatibility with our design in the opto isolator board. We reevaluated the design and decided to move to this off-the-shelf high-side switch.
I'm Amr Musa. I'm a graduate student in the computer science department at NC State, and I'd like to talk to you a little bit about our software system and how we designed it. Because gate, path, and buoy all require vision processing and object detection, we spent a lot of our focus and effort on creating computer vision algorithms to tackle tasks. One of the most successful ideas that we had that I want to point out was using a vision-based machine learning approach. Now, our team struggles with collecting data for machine learning, which is why we've avoided it in past years, because we can only collect data every so often, and it's always in the same area, the pool at NCSU, so we can't collect that much data. So this year, we tried a cutting-edge approach that's been tested in research papers around the world called sim to real. Now, what that involves is taking simulation data and passing it into your machine learning model along with real data with a little bit of biasing. And what that allows us to do is create a much more diverse set of training data and have a more effective algorithm. When we implemented our sim to real approach and tested it in our real environment, as you can see here, the results were pretty good. We were able to detect each side of the gate pretty reliably in our pool.
Hi, I'm Christopher Morey. I am a senior in electrical and computer engineering here at NC State, and I'm the acoustics sub-team lead. In order to accomplish Octagon at this year's competition, a robust acoustic system needed to be developed such that we could then hear the signal from a pinger and then determine the proper location of it relative to the robot. In order to do this, we had a hydrophone array with a set of vertically and horizontally spaced hydrophones that then sent their data to analog circuitry such that it could be filtered, amplified, and then logged at a picoscope, which is a type of oscilloscope, and then sent to a computer, whether that be a Raspberry Pi or a Jetson Nano for processing. So on the hardware end of things, our hardware circuitry consisted of a Chebyshev filter topology with cutoffs between 25 and 40 kilohertz. This corresponds to the frequencies we can expect at competition. Additionally, we have amplification on board that makes it so our signal is more clear when it's logged by the computer. In general, this amplification is going to be between about 22 decibels and about 40 decibels. On the software end of things, we have to have a system that can determine the difference of time between each of our sets of hydrophones. We do this via a cross-correlation algorithm that essentially runs the two signals across each other and finds out at what point in difference of time they're the most similar. This method allows us to reliably and accurately get the difference of time of arrival between pings in our two sets of hydrophones. This data can then be sent to a FFT to determine if it is the correct signal that we should be paying attention to, and then is sent to a specialized algorithm that estimates the pitch and yaw of the pinger relative to the robot via the time difference of arrival from the horizontal and vertical set of hydrophones.
With all of our subsystems and subteams working together, we believe we've created an AUV that's ready to compete and do well in RoboSub 2022.